Hi, this is Sai Potana, founder at Embedded Systems AI LLC. In this video, I'm going to go over how vLLM loads extremely large language models from storage into GPU memory and prepares them for high throughput inference. Modern frontier models can contain tens of billions of parameters, hundreds of gigabytes of weight, multi-GPU tensor parallel layouts, quantized representations, LoRa adapters, distributed checkpoint shards. Loading such models is no longer a simple file read operation. It is effectively a distributed system pipeline involving storage systems, deserialization, GPU memory management, quantization, tensor sharding, communication topology, and runtime memory planning. Large language model checkpoints are typically stored as multiple shards rather than one giant file. A 70 billion parameter model may contain dozens or hundreds of shard files. Each one could be of several gigabytes in size. Sharding solves several problems. Very large models exceed file system and memory practicality for single files. Multiple workers can load shards in parallel. Distributed training frameworks already produce sharded outputs naturally. Safe tensor is important because it is memory mappable, it supports efficient zero-copy reads, it improves loading security and speed. This makes it ideal for production inference systems. Multiple workers simultaneously read checkpoint shards, deserialize tensors, and reconstruct parameter layouts. This is often highly I/O-bound. Each tensor is reconstructed from serialized storage into runtime tensor objects. For example, attention projection matrices, MLP weights, embedding tables, normalization parameters become GPU-compatible tensor structures. Immediately after deserialization, weights are partitioned for tensor parallel execution. Instead of every GPU storing the full model, layers are split across devices. Examples include splitting attention heads, partitioning MLP columns, partitioning output projections. This dramatically reduces per GPU memory requirements. Each GPU rank receives ownership of a subset of tensor shards. For example, GPU 0 may own attention heads 0 through 15. GPU 1 owns heads 16 through 31. During inference, GPUs cooperate to reconstruct the logical full operation. Quantization is another important step in model loading. I've created another 10-minute video exclusively focusing on quantization. It's in my channel under vLLM series. Coming back to the slide, rather than loading weights in full precision, like FP16, BF16, they can be converted into GPTQ, AWQ, FP8, int8, int4 representations. Quantization reduces GPU memory consumption, memory bandwidth pressure, and inference latency. This is critical for modern inference workloads as memory bandwidth is limited. After sharding and quantization, tensors are distributed across GPU ranks. The device determines which GPU owns which layer, which rank executes which operation, how communication occurs between GPUs. The device map acts like a distributed placement table. It maps layer names to GPU ranks. For example, embedding layers to GPU 0, transformer layers spread across GPUs, final LM head on another rank. At runtime, tensor parallelism requires GPUs to cooperate continuously. Operations such as all reduce, all gather, reduce scatter combine partial tensor results across GPUs. Communication bandwidth becomes extremely important here. Inference performance depends heavily on link topology, PCI bandwidth, GPU interconnect latency. Poor communication topology can bottleneck the entire model. GPU memory is divided into regions: model weights, KV cache, activation workspaces, temporary buffers, runtime allocator state. This slide shows how model weights occupy a large permanent memory region. Model weights remain resident for the lifetime of the engine. By contrast, activations are transient, KV cache grows dynamically, temporary buffers change every decode step. Reloading weights per request would be impossible. Instead, weights stay permanently loaded while requests come and go. KV cache expands and contracts. Decoding executes continuously. This slide shows end-to-end pipeline flow for model loading. Checkpoint shards are read from the disk, and then workers deserialize tensors in parallel. Tensor parallel sharding partitions weights. Optional quantization transforms weights. Shards are distributed across GPU ranks. Weights are pinned into GPU memory, and then the model becomes inference ready. The model config stores architectural parameters such as number of layers, hidden size, attention heads, vocabulary size, rotary embedding parameters. This acts as a blueprint for reconstructing the model. The weight map tracks parameter names, tensor objects, sharded ownership. This is essentially the runtime tensor registry. And the device map determines where each module physically resides. This becomes critical for tensor parallelism, pipeline parallelism, and communication scheduling. The LoRa registry tracks which layers contain adapters, adapter rank, scaling factors, and merge state. This enables dynamic LoRa loading and composition without modifying the model base permanently. Key algorithms used in model loading are tensor parallel sharding, checkpoint deserialization, quantization on load, and LoRa adapter merging. Tensor parallel sharding divides computation across GPUs. This allows models larger than GPU's memory capacity to execute efficiently. Parallel deserialization maximizes disk throughput and startup speed. Quantization reduces runtime memory footprint before tensors ever reach GPU execution. LoRa merging enables lightweight specialization of base models for fine-tuning, personalization, and task adaptation without duplicating full model weights. Memory diagram explains how GPU memory is organized after loading completes. At the bottom, there is CUDA context, runtime allocator metadata. Above that, pinned model weights, and then paged KV cache, and then comes activation buffers and workspaces, and finally, temporary runtime buffers. KV cache is dynamic and it grows based on sequence length, active requests, and batch size, while model weights remain fixed. Shared memory resource creates the central challenge of inference serving, balancing permanent model residency with dynamic runtime memory allocation. To sum it up, model loading is often overlooked, but it fundamentally determines startup latency, memory efficiency, maximum model size, multi-GPU scalability, quantization capability, and adaptive flexibility. Modern inference systems spend enormous engineering effort optimizing this pipeline. Thank you.